Hey folks, this week we are going to be learning about momentum and impulse. There's going to be a lot of information for you guys to read on the sheet. I'm not going to read through it all because I don't want to waste a bunch of your time. So if you can download the PDF, give it a read through yourself so you can understand all of the finer points. I'm going to just highlight some of the big ideas. So with momentum has two properties that it relies on. Momentum relies on mass and velocity of an object. So Newton liked to describe momentum as a quantity of motion, so it's how it can describe what an object is actually doing as it's moving. So the mass and velocity impacts an object's momentum. If it has a high mass, it will have a higher momentum. If it has a low mass, it will have a lower momentum. A high velocity will give it a higher momentum. A lower velocity will give it a lower momentum. For whatever reason, we use the symbol of a small or a lowercase p to signify momentum. We do have a formula for calculating momentum, and it relates directly to the two properties of momentum, which is its mass and velocity. So we say that momentum is equal to its mass multiplied by its velocity. Or, since P stands for momentum, we can say P is equal to m times v. So we can apply some mathematical values to this. Say we had an object. Say we had a kettleball, like those things that are like basketballs but less fun because they're heavy. Say we had a 2 kilogram kettleball that was traveling at 10 meters per second. 2 kilograms would be its mass. 10 meters per second would be its velocity. So if we wanted to calculate that kettleball's momentum, we would say P equals m times v. P equals, substitute in your values, 2 times 10. And our momentum is going to end up being, in this case, 20. Awesome. The second part of this is impulse. Now, impulse is what we need to change momentum. So, the two things that come into impulse is the force that's being applied to the object and how long that force is being applied for. So, to calculate impulse, we use the formula of impulse equals force times time force is applied for. So I, impulse, equals force, F, times time applied for, which is change in t. Now, impulse and momentum are going to be equal. So if an object, let's say that kettleball, had a momentum of 20, to change that kettleball's motion from 10 meters per second all the way down to 0 meters per second, we would have to apply the same impulse as was its momentum. So since the momentum was 20, we would need to apply an impulse of 20 to stop that. So an example of a way to achieve that impulse is if we know that impulse is equal to force times change in time. Say we applied a force of 5 and we applied that for, that's going to be 5 newtons, and we applied that for 4 seconds, we would end up with an impulse of 20. Which is exactly the same as the momentum, so it would make that object stop. So that's what we're talking about down here. So in order to change momentum to 0, so to stop it, or to change a momentum from 0 to make it move, you have to have the momentum equal to the impulse, like we had here. Now, where we use this momentum and impulse a lot is in vehicle safety. So the reason we use it in vehicle safety is, since an object like a car has momentum when it's moving, you're going to have an impulse to stop that movement. So if an object is applying its brakes, it's going to apply an impulse, which is a low force over a large period of time. But if it hits a wall, it's going to have a short period of time, and the force is going to be very high to achieve that impulse. Now, my little example for that is going to be between a textbook and a piece of paper. Now, you may have heard of cars having crumple zones, and you'll be able to read it in your booklet. We have a crumple zone section. But my little demonstration here is this textbook doesn't have a crumple zone. It doesn't crumple, it just stays stiff. So if it hit a wall, which is going to be my hand here, it's going to almost immediately stop. So since the time is so low to make it stop, the force on the book is going to be high. But if we had this piece of paper, which is more bendy, it can actually crumple. The time it takes to stop when it hits the wall is going to be increased because it crumples as it hits the wall. So you may have heard people say that cars nowadays just aren't made like they're used to, because if you get in a low-speed crash, they still crumple right up and they look like they really didn't hold out on the crash very well. But they're actually built that way because the longer it takes to come to a stop is the less force that's going to be applied to the individuals in the car.